All right, let's do a reaction problem that has biomass synthesis in it. So for this problem, we are looking at a denitrification tank. And what that tells us is that nitrate will be our electron acceptor. And we're going to be adding ethanol as an electron donor and carbon source. All right, so first of all, we're going to go to our table of half reactions in our book. And from there, we're going to pick out our ethanol equation. So our RD, or our electron donor equation, will be for ethanol. Notice that because everything's written as a reduction in the table, that you're going to be looking for ethanol on the right-hand side of the equation. So we pick up this equation from our book, 1/6 CO2 plus proton plus electron goes to 1/12 ethanol plus 1/4 water, H2O. Okay, so we've picked up our electron donor equation. We're going to pick up our cell synthesis equation. And so we would have to be told which equation to use. And in this case, we're assuming that nitrate, because it's so available, will be our nitrogen source for the cell synthesis. So we can go and find our RS equation, which should be this one. And this gives us 1/28 our C5H7O2N, which is our biomass. And then we'll add on the waters at the end. All right. Okay, so now that we have that, the next equation we're going to pick up is going to be our electron acceptor equation. And so we have nitrate as our electron acceptor, so we're going to look for that equation on the table, and we'll find this equation, 1/5 nitrate plus 6/5 proton plus electron goes to 1/10 nitrogen plus 3/5 water. Okay, and so we're going to assume a few things. So first, the assumption that we used for our cell synthesis was that nitrate was our nitrogen source for cell synthesis. And then we also, let's assume that our Fe is 0.41. All right, so if our Fe is 0.41, our Fs, so the amount of electrons or fraction of an electron equivalent that goes to cell synthesis, will be 1 minus 0.41, which is equal to 0.59. All right, and then we have this equation right here that brings it all together. Our overall equation is equal to Fe times our Ra equation plus Fs times our Rs equation minus Rd, which is our electron donor equation. And the reason this is minus is because we are going to need to flip this equation around because we need to have our acetate, or excuse me, our ethanol on the left-hand side of the equation here. All right, so first things, I like to kind of calculate these things separately. So we'll do Fe times Ra will be equal to, and so this is basically just taking this 0.41 and multiplying by this equation right here, this Ra, and we should get something like this, 0.205 nitrate plus 0.492 proton plus 0.41 electron goes to 0.041 nitrogen. And make sure that you can see everything I'm writing here, plus 0.246 H2O. So I'll move that maybe a little bit over here so that you can see all of that. Okay, so we've got that. I'm going to calculate now the Fs times our Rs equation, and that comes to 0.02107 nitrate plus 0.1054 CO2 plus 0.611 proton plus 0.59 electron, and that all goes to 0.02107 C5H7O2N plus 0.2318 H2O. All right. And then next we're going to have our negative RD, because we're going to just add all of these up, and so we want to make sure that, you know, we have that negative. And so when we multiply by -1, what that means is that we're just flipping the reaction around. So here we end up with 1/12 of our ethanol plus 1/4 H2O goes to 1/6 CO2 plus a proton plus an electron. Now if we say add up these things right here, then we should get our overall reaction. So just to double check, I like to look at our electrons. We've got on the left-hand side 0.41 electrons and 0.59 electrons. So if we add that up, it should be 1 electron. And sure enough, on the right-hand side, we've got 1 electron to match, so we know that our electrons will cancel out. So that's just a good double check for us before we go ahead and write the final reaction here. And so our final reaction will come out to, and you know, there's some terms that will have to be canceled and so forth, but this will be our final answer here. So we'll have 1/12 of our ethanol plus 0.226 nitrate plus 0.103 proton plus 0.2278 H2O, and that all goes to 0.0613 CO2 plus 0.041 nitrogen plus 0.02107 C5H7O2N. All right, so this is our overall final equation. It includes the fact that we have our ethanol going in, we've got our nitrate going in, and we're resulting in some CO2 production, but we're also resulting in some biomass production with that carbon. And then finally, we have nitrogen that's going and being converted to our nitrogen gas from nitrate. So this is our overall equation. If we were asked, for example, what is the yield coefficient or biomass yield, if you will. Y. We can calculate that. And so let's switch to a new sheet here. So we'll move this up so we can keep the full equation in our view here. So the first thing we're going to do is look at kind of the definition of our yield. So our yield is equal to grams VSS per gram COD, right? And so if we can move that up just right there. So this is our equation for the yield. And so what we can do is we can look at our overall equation up here and we can pull out some things that are useful. So for example, let's pull out the moles of biomass that's produced here. So we have our 0.02107 moles of our biomass, C5H7O2N. And we'll divide that by our moles of our ethanol. So we have 1/12 mole of our electron donor ethanol. So this is what contributes to the consumption of COD. So this is really COD consumed, if you will, VSS produced. And so in this case, because we're considering theoretical, we're only considering based on this equation up here, how much biomass will be produced versus how much COD is consumed in the form of ethanol. All right, so now we have to get from this moles of biomass to grams, and then we also have to get from moles of ethanol to grams COD. So first, let's work on the top part. Our molecular weight of our C5H7O2N is 113 grams per mole. So that one's fairly easy. So now we're able to, when we come back, convert this moles of biomass into grams of biomass, or grams VSS. And then now we need to convert and be able to convert this ethanol into grams COD. So to do that, we have to actually look at a different set of half reactions. So if we look at our half reaction for our ethanol, so we have 1/12 CH3CH2OH, that's our ethanol, plus 1/4 H2O is equal to 1/6 CO2 plus proton plus electron. So this is the equation that's straight from the half reactions, but it is flipped so that we have our electron donor on the left-hand side here. And then we can also pick up this equation from the book, 1/4 O2 plus proton plus electron is equal to 1/2 H2O, and that's, you know, a pretty familiar equation to you probably by this point. And so because they're both already in terms of one electron, we can go ahead and add that. And what we find is we get 1/12 ethanol plus 1/4 O2 goes to 1/6 CO2 plus 1/4 H2O. Now we can figure out the COD of the ethanol. Using this relationship here, so we know we have 1/4 mole O2, and we know our molecular weight of O2 is 32 grams O2 per mole O2. Then all of this per mole of ethanol. And so if we kind of do that calculation, our COD of our ethanol is equal to 8 grams COD, or 8 grams of O2 required per mole of our CH3CH2OH ethanol. So now we kind of have this relationship right here that we can use along with this relationship up here to calculate what our Y is in the correct units. So our Y in terms of grams VSS per gram COD is going to be 0.02107 moles of our biomass, C5H7O2N, times our 113 grams per mole of that. And then we have 1/12 moles of our ethanol here, times 8 grams COD per mole. And then we can do that calculation, and we should get Y is equal to 3.57 grams VSS per gram COD. So based on the stoichiometry, we can figure out how much biomass in terms of grams VSS is produced per gram COD consumed.